Okay, so let's go. So here's the schedule for today.
Okay.
More or less.
You just have to get rid
Little
of
bit
it.
Did you
of
say
hairball.
more or less?
Yeah. So we'll go over the assignment, see if you have any questions on that. And we'll just go over the quiz. And then we got kind of like this last kind of summative thing about reactions taking place and not taking place, and got an assignment on that, and then we're good. So that's kind of the story. All right, so let's chit chat. So on 26, where, and this is going to be, well, let me go ahead, I'll just go ahead and give you this, that way you have it so you'll see it. What I'm going to give you is like another redox table, but this has a lot more on it, because the redox table that you guys have just has like elements. This has actually like compounds that can act as oxidizing agents or reducing agents. So let me go ahead and hand that out, which is the same thing that I have up here, and then that way you can see that.
It's not hard for me to get the reductions. The reductions are the easy half of the redox, half redox reactions. It's the oxidation I have trouble with. Does that make sense?
Okay. So here's what we've got. So if you look like on number 26A, where you have NO2 and dichromate, and that's going to roll into Cr3 plus NO3. So one of the things, and here's like this dichromate potential. So you have dichromate over here that has like a very distinctive bright orange color. Okay? So here you have dichromate, right? And this has to be done in an acidic environment, mainly because of the fact that if you look at the, and the cool thing about this is that this is already balanced, okay? It's already balanced. Now, the other thing that you'll see, this chart has slightly different values than some of the ones that you have on that, on the one you're used to dealing with, okay? So I kind of had both answer keys worked out, but you can pick either one. So, like, that dichromate one isn't on your standard reduction table, because that just has all elements. So this is like a broader list of half reactions. So basically, you have dichromate over here. So, party girl, since dichromate's on the left side, kind of up here towards the top, right? So do you think dichromate is a good oxidizing agent or a good reducing agent? Why? Beautiful, okay? So what you should be able to do on this quiz is first off, look at dichromate and figure out, number one, what that oxidation state of that chromium is, okay, within that dichromate. Oh, okay, oxygen 2 minus. Oh, that gives me negative 14. That has to be 12 plus. There's 2 of those. That has to be 6 plus. There's 2 of those. This is why we gain 6 electrons. Now, so dichromate, basically what that means is that it really, really, really wants to take in electrons. Now, so if you look at what would physically happen in this reaction, because dichromate has a very distinctive orangish color. So if you run this reaction, what you would see is that the dichromate, if you started with that, and then you added nitrite to it, which is NO2, if you started with that dichromate, it would start orangish, and then as you added more and more NO2 to it, that color would fade, okay? And it would become less and less and less orange. So that's one of the things we're going to do next on this big lab with potassium permanganate. As you all saw, potassium permanganate has a very distinctive color to it. Okay, so it's really, really dark purple. So you can use that as an indicator because if permanganate ions are in the solution, then it's going to have that very, very distinctive color to it. Okay, so basically you're going to go through, you have the reduction, you figure out the reductions, the oxidations, you're going to add those together. Like I said, on number 26A, you should end up with 4 waters on the product side, if that goes well. And then on 26C, you should end up with 11 waters on the product side, if all goes well. And make sure on number 30 you have the terminology right, because if 30A is wrong, everything else is going to be wrong. So you should realize on 30A that aluminum is being oxidized and the nickel is being reduced. Because if that's wrong, everything else is going to be wrong. Okay? So on 30A, your aluminum is oxidized, your nickel is being reduced. And then you're off to the races. And no, there won't be anything about these cells on the quiz. Okay? You won't have to do a cathode, anode, or anything like that on the quiz. Okay? All right. Anything specific on the assignment you want me to go over? Going once, going twice. So, okay, so on the quiz, and no, there's not a backside to it, okay? Just 6 questions. So, on number 4, I've got this big one with bromide ions, okay? Rolling into MnO4. And so, I want to specifically see the reduction half reaction written out, the oxidation written out, and then the sum when you add those together. Okay? So I specifically want to see those 2 half reactions. On number 5, I want you to write the net ionic. In other words, if it's a spectator ion, I don't want to see it. But if you want to like work your way through and write out like the whole thing and then cross out your spectator ions, that's fine. But at the end of the day, what I want is just the net ionic equation, okay? So if they're spectator ions, I don't want to see them. So, okay, kids. So, let me stop that camera.
Some iron,
Some iron, right? Yeah, why iron?
because it has a lower voltage.
Yeah. So,
Good job, buddy.
here's the deal. So what we're talking about is that we have AuCl4 and we're trying to get the gold to form out. And I just asked Mr. Carter which element that he would choose. So what would happen is that if he took a chunk of iron, right? If he took that chunk of iron and he dropped it in that solution, here on an atomic level, this is what you would see. In that beaker, whoop, that's not what I want. In that beaker, you would have these AuCl4 ions floating around. And he would drop in a chunk of iron. So on an atomic level, what would you see happening? Here's your chunk of iron. What's that iron going to do? It's going to dissolve, right? It's going to start going into the solution. So those 3 electrons, okay, are going to be given off, right? Now, then what's the gold going to do? The gold's going to take in those electrons, and just like yesterday, when we passed that around, when we had that, I put that piece of copper in with the silver nitrate solution, and the silver formed, and that solution turned to nice blue copper because those copper ions were going into the solution. Same thing's going to happen here. So what you would see is that you would see the iron dissolving, so the mass of the iron would decrease, but then you would see the gold forming on that metal. Okay? So you would see that change taking place. And you could use anything down below. You could use iron. Sodium would probably be a little dramatic, you know, because sodium would probably react with the water before it did anything else.
What about aluminum?
Could do aluminum, okay? Any of those are low. Now, what she couldn't do is that she couldn't dump in like anything up here, okay? She couldn't dump in number one, she wouldn't want to use elemental bromine, because if she used elemental bromine, then you would have two reduction reactions taking place, so you never have a reaction, okay? So elemental bromine wouldn't do any good, nor would adding sodium bromide, because if she just added sodium bromide, and she'd have the bromide ions, well, what happened then, this would get reversed, so you'd have negative 1.09 plus 0.99, you'd end up with a negative E naught value. Guess what? The reaction wouldn't take place. So she couldn't add anything up above, okay, because it wouldn't be spontaneous. Anything down below, now again, here's the difference. There's a big difference between saying, oh, I'm going to add iron. Well, are you going to add Fe2 plus ions, or you're going to add elemental iron? That's what you have to keep straight, okay? Because if you just add Fe2 plus ions, what's going to happen? Nothing, okay? Absolutely nothing's going to happen, because you're going to have two you're going to have two reduction reactions. You drop in elemental iron, now you're talking. So that's why it's vital that you keep track of which one are you talking about, okay? Now, here's another classic way that these questions play out. So let's say I gave you this question. Basically, are hydronium ions capable of oxidizing silver? Now, typically how this plays out, they stop it with the silver part. But it's implied that it's going to turn into Ag+. So here's the situation. If I take a chunk of silver, okay, so maybe a silver I've got in my pockets. If I drop it, here's the question. If I drop a dime into a solution of hydrofluoric acid, is anything going to happen?
Oh, I see.
I don't know. You tell me. Again, you can play the mathematical game, you can play the over-under game.
So you're taking elemental silver and dropping it into?
I'm dropping a chunk of elemental silver into a solution that has hydronium ions, maybe nitric acid, hydrochloric acid, even water, because water has some hydronium ions in it.
Okay.
Acetate, what are your thoughts?
Well, I'm looking for hydrochloric acid.
No, don't look for hydrochloric acid.
Okay.
Focus on the hydronium ion. Because the chlorine isn't going to do anything. The anion isn't going to do anything.
Yeah. But I'm thinking no,
Why are you thinking no? You would be correct to think no.
because Ag ions want to go to Ag, but Ag does not want to go to Ag ions.
Okay. So if you play the over-under game, right? So in the middle you have two hydrogens, right? Gaining 2 electrons. Turning into elemental hydrogen gas, right? So here's the fundamental question on the tug of war. Is this proton, and that's what it is, if you take a proton and put it beside silver, is that electron going to jump from the silver to the hydrogen? That's the fundamental question, okay? Now, Tay, you said no, because where is silver in relation to hydrogen?
The very top.
Is it above or, let's play the over-under game.
Yeah, it's above.
It's above, right? So the silver would have to turn into Ag plus and an electron, okay? That's what would have to happen. So that reduction equation would have to get switched,
So
right?
oxidation.
So yeah, so the silver would have to turn into an oxidation.
So it'd be negative.
So that would be negative.
Okay.
The hydrogen is
0.
0. So you'd have a negative E naught value. Guess what?
It's not going to happen.
It's not going to happen. Okay? You're going to have a negative E naught value. If you play the over-under game, where is silver in relation to hydrogen?
Above it.
It's above it, right? Okay? Not gonna happen. Now, this is why we use silver in jewelry, because this reaction doesn't happen, okay? If this reaction happened, you wouldn't use silver in jewelry because of the fact that you put it in any kind of acidic environment with any number of hydronium ions, it would dissolve and form silver ions, okay? That's why that's why we use silver in jewelry. Now, are hydronium ions capable of oxidizing zinc?
Yes.
Yeah.
Why?
Because it's going to be a
above
positive E naught value.
It's going to be a positive E naught value. Where's zinc in relation to the hydronium ions?
Under it.
Under it. So if you play the over-under game, okay, it's below it, hey, the reaction's going to take place, okay? See the pattern. So where we're going with this. Okay. Now, it's the exact same format of the question, but it's completely different. So is hydrogen gas capable of reducing silver ions into silver? So in other words, if I had a beaker, like I had yesterday with silver nitrate in it, and I bubbled hydrogen gas, so I had a reaction and I had some hydrogen gas, and I bubbled hydrogen gas into this beaker, okay? Here's the question. Would that hydrogen gas reduce the silver?
Yes.
This one will. Why?
Because it has a positive E naught value.
Because silver, now here's the difference. Here you had the silver ion reacting with elemental silver, okay? It's still hydrogen and silver, but it's a completely different scenario now. With this one, now I've got hydrogen gas, okay? So I'd bubble in hydrogen gas into the beaker. It would have silver ions. I got a solution of silver nitrate. So if you say yes, which you should, so what's going to happen is that over a period of time, you would begin to see silver form on the bottom of the beaker, okay? Because a little bit of that silver ion each time would take an electron and form a solution. Now, if this happens, and it does, think this through. What's going to happen to the pH of the solution as time goes by? Why?
Because the hydrogen gas is losing its electrons between hydrogen.
Yeah, so if you look at this reaction, if I asked you to write the net ionic equation for this reaction, it would be Ag plus H2, right? And you're going to get elemental silver and hydronium ions, right? So now you got to balance it. So I got two hydroniums, got that. Then I need, but now here's what you have to watch. So I got two hydronium ions over here, right? So that's cool, balances that out. But now I need to balance out my charge. So when you do net ionics, you also have to balance out charge. So right now, I've got two positive charges over here from the one positive charge over here. So what do I have to do? Well, I need to put two silver ions over there, but then what do I have to do?
Multiply the other.
Then I got to put two over there, okay? So this is why when you do half reactions, you have to balance it with charge, and you have to balance it with number of electrons, okay? So yeah, so this would happen, okay? So hydrogen gas in a solution of silver ions would plate out silver, okay? Now, is Cu2 plus capable of oxidizing zinc? So what would this physically look like? If I asked you to go set up this scenario, what would you do?
Copper nitrate.
You get some copper nitrate and
A block of zinc.
a chunk of zinc. Okay, you would physically go get a solution of copper nitrate, dark blue color, and you drop in a chunk of zinc. Okay. Now, if this reaction takes place, what's going to happen to the color of that copper ion? What's going to happen to the color of that solution?
It's going to go clear.
It's going to fade, right, because the copper ions are being used up. What's going to happen to the concentration of the zinc ions?
It's going to go up.
It's going to increase, okay? So, what's going to happen here? What do you get? Will this reaction take place?
Yes.
Yes, you do the over-under game. The Cu2 plus is going to take those electrons from the zinc, and this reaction will take place. But, if I dropped a piece of copper into a solution of zinc ions, same elements, both copper, both zinc. Now what's going to happen?
There's gonna be no reaction.
Absolutely nothing is going to happen. Okay? Absolutely nothing. What you would see is the zinc, the copper would just sit there. Okay? Because if you look at this from an energy perspective, the Cu2 plus and the zinc, Mother Nature likes that because Mother Nature is going to end up at a lower energy state. This one, the zinc with the copper, it's already at the bottom of the energy well. Mother Nature lays the prima donna and says, I don't think I want to do that today. I'm just going to sit here in my tie-dye dress and smoke some hookah. You all just chill out, okay? Because it's already at the bottom of that energy well. So there's nothing to be gained. All right. Got that? Okay. So let me hand out your assignment, and don't flip out. I only want you to do the ones that are circled. Okay? So don't flip out and go, oh my God, we have to do all of these. No. You only have to do the ones that I have circled.
Thank you.
Okay? So I didn't want you all to have heart attacks. So stop that for a second. Okay. So listen to me on this assignment. Only do the ones that are circled,
Yes, sir.
but read the instructions. So if you look on 35, it says calculate E naught from the following cells, right?
Okay.
So I would, if I would use the blue one first, the one that you're used to working with, okay? Because it's simpler to sort through those because those are the ones that have just the elements on them. So notice on these you want to calculate E naught, okay? Balance it if you have to, okay? There you go. Now, the same thing on 36. Calculate E naught. Which ones are spontaneous? Meaning that you're going to have a positive or negative E naught value. Positive, okay? So basically you're going to say, hey, here's this equation. Here's my E naught value. Is it spontaneous or not? Okay? So those are the 3 bits of information you want to give for those 4 reactions. Okay? Spontaneous, E naught value, overall balanced equation. Now, when you get to 36, because it has MnO4, now you've got to use that, the one that I just gave you, because the MnO4 E naught value is not on the one that you had before. So this is why you have to go back and forth between the two. Now, on 47, okay, says, place the following in order of increasing strength as oxidizing agents. Now, think this through. Increasing strength, right? Oxidizing agents. What do oxidizing agents want to do?
Reduce.
Meaning they want to do what?
Turn it.
They want to
Take.
gain electrons, right? They want to gain electrons. So basically, when you get done with 47, you wanted an increasing strength. So the last thing that you list is the one that is most willing to take in electrons.
Okay.
Okay? The first one that you're going to list is the one that is least willing to take in electrons.
Okay.
Okay? Does that make sense?
Yeah.
Now, when you get to 49, okay? When you get to 49, answer the following questions. Is hydrogen capable of oxidizing Cu into Cu2 plus? Okay? Again, this is just kind of what we went through. All right? Now, when you get to 50, same type of thing, but only do A, B, and D on 50. So then, when you get to 51, now you have to pay attention to what's happening on 51, okay? Notice that you have zinc ions and you have zinc. You have sodium ions and you have chloride ions, okay? You have silver ions and you have silver. So basically on 51A, I'm saying which is the strongest oxidizing agent, okay? That's what you want to know. Which one is the strongest oxidizing agent? So basically, what am I asking you to find?
The ion, the strongest oxidizing ion.
Well, if it's an oxidizing agent, what does it want to do?
Reduce.
Which means that it wants to
Gain.
gain electrons, okay? Now, so do you think Ag, let's think this through. Do you think elemental silver would be a good oxidizing agent? Because if it did, if you said silver was a good oxidizing agent, what are you telling me that it's willing to do? Which means it would do what? So if it gained an electron, you would end up in Ag1 minus.
No.
Have you ever seen Ag1 minus?
No.
No, you know why?
Doesn't exist.
Doesn't exist, it's not stable, okay? So silver would be a horrible oxidizing agent. Elemental silver would, okay? It would be horrible as an oxidizing agent. Wouldn't even happen at all, mainly because the silver is at the bottom of the energy well. Now, when you get to, on 51, when you get to C and D, it is very possible on C and D on 51 that you're going to have more than one possible answer, okay? So keep that in mind when you get to 51, C and D. All right, I'm done. You're on your own.